All right, so with the quiz yesterday, we kind of wrap up chapter 5, which is the introduction to the integral and the definite integral. And, you know, we kind of went through a process there in chapter 5 where we said, okay, what is area, what is definite integral? And we started with geometry, shapes, and we said, okay, we find the area. We define this squiggly line and the notation just that means area of the curve. But we kind of got into distance and velocity and how the area under the curve could be the distance traveled. So kind of gave a rationale why we might want to do this area business. And we started that like the second day of class, you know. And so then we investigated a little farther. Then we said, let's look like what we did with the derivative. How we made this function called the slope function, right? We said that we could measure the slope at this point, then at this point, then at this point. We could plot those points and make a derivative function, a slope function, and we call that f prime. And then we saw those connections, and then we got into the whole f of x plus h minus f of x, and we found out, oh my God, x cubed, the derivative is 3x squared, and you know, And we had all these equations for slope, and then we said, well, if slope measures the rate of change of a function, what can that do for us? We got into max and mins, where the slope is 0, where the rate of change is 0. That might be important. Finding a high spot or a low spot on a function, that might be a big deal. We got into related rates. We got into, you know, all these different types of problems that might involve rate of change. So we said, well, maybe area. Maybe we can do something similar with area, right? And we can do this. So we took pieces of area and we changed the right endpoint, right? And we said, okay, the area from here to here, and then from here to here, and here to here. And let's plot those areas. And lo and behold, what did we find out? That the area function was what? If you did the area function under the x, y equals x graph, what was the area function? 1/2 x squared, right? The antiderivative. Yeah. And so, okay, there's this connection. So that was what we did in the beginning of chapter 5. Then we said, okay, if we do what we did with slopes and make an area function, it's the antiderivative. Oh, the antiderivative is related to area. That was a big deal. Matter of fact, it's what ties the two together. It's the fundamental theorem of calculus. And we use that to come up with this part right here, fundamental theorem part 2. So we can find the area under any shaped curve if we know its equation and it has an antiderivative. So we got into that. And we said, okay, antiderivatives must be pretty important. So we spent some time doing antiderivatives, right? And taking the antiderivative gateway test and being able to do that. Also, we can do this kind of stuff right here. Of course, now that we know how to do it, 90% of the time you're going to use your calculator to do those integrals anyway. Okay, but that, you know, it's kind of like learning your times tables, but now if you have to do a big long multiplication, 4-digit multiplication that's used to practice in 3rd grade or 4th grade or whatever, you know, now you just type in your calculator, right? But you know how to do it. You have a number sense, you know, about it. Hopefully you understand it. And then, so now we finished up here and just took this quiz yesterday on what happens if we can't do the antiderivative. What if we need to approximate the integral? What if we need to do left rectangles, right rectangles, midpoints, trapezoids? So we did a little bit with that. Okay, so that's kind of a quick little synopsis of where we've been throughout the whole year and how everything kind of ties together. All right, now we're going to go into chapter 6. Chapter 6 is a short little chapter that gets into a little more detail, a little more depth of left rectangle approximations, rights, midpoints. How are they off? And how much error do they commit? How does the calculator do an area when it can't do this? How does it approximate it and know how exact it is? So we're going to investigate that a little bit for a couple weeks here. Leading up till spring break, okay, and try to finish that off. So it's a pretty short chapter. Then after spring break, we'll get into the different applications of the definite integral. But we're going to see that we already kind of know some already. And so we're going to spend today just kind of, before we dive into a little more with just these techniques here, we're gonna kind of go back and kind of summarize what do we already know kind of about the integral and fine tune that a little bit. And then you're going to see that's going to be helpful in these packets. Okay, like especially the one with the tables, you know, some of those questions that it asks, you see a lot of those going over and over. So, in your notes, so this is nothing new, and in the red here I put calculator because what I'm telling you is a lot of the time, you're still going to have to do this by hand some. We still have no calculator parts of quizzes. We still have the no calculator part of the final EP test. So you're going to have to be able to do this, have to be able to do these by hand. But most of the time, we'll get to use our calculators to help us a lot on those things. All right, so with that, let me pass out another packet. Yes. All right, so those of you listening at home, this is the 2016 free response questions. So these are the actual test, free response questions from 2 years ago. And let's turn to 6C. All right, so here would be an example of just a problem. So we'll go ahead and do this. At some point, we'll hopefully do all of these problems in this packet. Okay, either together or you'll just do them on your own. Okay, so 2016 6C, we have a definite integral right here. Okay, now I would say first of all, and not that you would totally do this, but you see, okay, yeah, we got a table up here. But really, okay, we're going to have a table. We're going to have to plug some values in. But really, to start this, we're just going to do work down here. It doesn't really matter what's up there, right? What are we going to do? We see a definite integral from 1 to 3. It says f double prime right here. There's a 2 in there. Okay, we'll have to deal with that. But this is just going to be an f of b minus f of anything. It's just antiderivative, right? So what am I going to write down right here? What do you think? Now, the 2 is a little bit of an issue, I suppose. I'll tell you what, let's do this. Well, if I gave you, let's just go back to the fundamental theorem part 2. Fundamental theorem part 2 says this, right, from A to B, right? And so what do I put over here? Big F of B minus big F of A, right? Now, actually, the way we did that is we did the antiderivative. The step I'm leaving off is we do the antiderivative of this, which would be big F of X, and then we do right bracket, and then we do A and B, right? That's probably the step I'm leaving off. We would normally, if I gave you the antiderivative of x squared dx from 1 to 3, we would do 1/3 x cubed, and then we would go like this, and we would go like that, right? So let's do that down here. That would be helpful. Because we got this 2 in here, that's going to cause us a little bit of an issue. Okay, so let's do that first. Okay, so let's just look at that and let's say, what's the antiderivative? F prime, and what else? Almost got it. And we're going to have a 1/2 out there, right? We're going to have to kick out a 1/2 because of that 2 in it, right? We've done that. We've done that. You got a 2 on the inside, you have to take out a 1/2. F double prime, the antiderivative is F prime. See, so what we're going to get into now, especially as we go through the packets, is, and the book stuff will come along with it too, okay? But we're a long ways down the road. You know, people, some of the juniors I know that are in honors math stuff are worried about, you know, calculus, and you guys shouldn't, you know, add to their worry. But calculus only go in 2 terms. And some people might say, good, geez, thank God, I would have taken it if it was only 2 terms. I didn't want to go 3 terms. You know, whatever. So maybe it's better. But you know, if push really came to shove, I mean, if we had to get done and we had to, you know, get ready for the AP test, I mean, we're not that far away. I mean, you go through the packets. I mean, there's a lot of stuff we should know how to do. Now, the difference between should know how to do and can really do well I mean, there's a kind of a gap there probably, right? So, there's some things that we'll be finishing up and doing, and the goal will be to really, if you want to take that AP test, to really get a 4 or 5 and really be able to nail it, and really, really feel well prepared for next year. And that's a big part of what's going to happen last term, right? Last term, of course, seniors did that a little early, so last term's a little shorter. It's broke up with spring break. We missed for various things. So it does allow us to not have to really push, the down, especially if they put it in the spring next year, they're going to be kind of pushing to get things done at a time when, especially if you're a senior, you may not be able to work around. We'll have the advantage to be able to slow down a little bit when we get to that point. Okay, but we're a long way. We've done enough of this stuff that we, even right now we've seen a lot of it. But there's a few things we have yet to do, and we would, they're going to have to cut out maybe some things that we did early on too. But anyway, I ramble on. But that's your antiderivative right there. That's your antiderivative right there. And then we just put a 1 and a 3. Right? So what are we going to have? We're going to have 1/2 f prime of, so show all your work here, right? You want to write this to this. So we're going to have 1/2 f prime of 6 minus 1/2 f prime of 2. And then we would just go up to our table. Right? So that's what this would look like, okay? So you've got a scenario like this. So I guess where I was going with that, kind of what I was talking about before, is a lot of what we're going to do is kind of like with the first set of packets for the midterm is, okay, now we got this basic knowledge about fundamental third part 2, but now we need to see it in a lot of different settings. We need to see it in a lot of different type problems, so when we look at that, we right away would think to do this, right? And we just haven't seen a lot of that yet. Okay, so anyway, f prime of 6 is going to be 5, so this is 5/2. And then f prime of 2 is going to be -2, so that's going to be -1. So 5/2 plus 1 would be 7/2. So the answer to that problem is 7/2. Okay? So that's how we would do 6C. Okay? All right, moving along. So that's just, a basic kind of, not a basic, I mean, it's not the simplest one we've done, but it's just using fundamental theorem part 2 to do a definite interval with table information, right? That's kind of our emphasis here with that packet too, is looking at some of this stuff with tables. Okay, so let's talk about applications. That's what chapter 7 is really going to be about. We're going to get into some more applications, but we already know some applications of definite intervals. Okay, so we're going to go through about 4 of them here, fairly quickly. We're going to use this packet to do them. Okay, so the first application of definite interval would be area under curve. Okay, so we won't really do it probably now. We've already been doing that. And you got a curve. You want to do the area under it. What's the area? Boom. We just do our fundamental theorem part 2, and we just write it down, and away we go. Okay, so that's the first one we learned. That's the first way we knew about a definite interval. Not much to say about that, right? Here's x squared. What's the area from 0 to 4? So you set it up, you do it. You got it. Okay? All right. The next one we learned is this one right here. Okay? You got to have this memorized. You got to have this memorized. When you see this, you've got to know this is average value of that function. Now notice, this is f, this is f. So if they want the average value of f prime, if the question asks for the average value of f prime, we would put an f prime in that interval, right? The f prime would go inside that interval. If they want the average value of f double prime would go in there. If they want the average temperature over a 365-day period, the temperature function would go inside that interval. Okay? Whatever function you're doing the average value of, that's what goes in there. Now, a lot of times you see it written this way, so be prepared to see this. A lot of times you'll see an integral 1/10, integral 0 to 10, okay, of f of x, right? And this is one of their favorite problems to ask on a AP test. They say, explain what this means in context of the problem, right? Well, it means whatever f is, whatever units f is, it's the average value of that function from, and whatever units 10, the time, maybe it's time, 0 to 10 hours, right? Or whatever the case may be. So when you see this, right? Now, a lot of you are going to think that 1/10, that's going to look like width when we were doing that width thing. That's not what that is, right? Remember, that was the dx axis here. This is just, they've just taken this 10 that's on the bottom, and they pulled that out in front like that. Okay, so just understand, a lot of times you see it written this way. Okay, all right, let's go to 2016, let's go to 5A. Okay, this was a problem they had. This was a problem that really freaked some people out. You're going to see, we're going to come back and do that one later on. Not this part, this 5A didn't freak people out, but the rest of it here, part B, and finding this volume, which is a little different than, I don't think our students had too much trouble with it, but I was asking kind of a strange way. The inside of a funnel has circular cross sections. At height h, the radius of the funnel is given by this, because the radius obviously is going to grow. So as h gets bigger, as you go up the funnel, the radius is going to get bigger and bigger. Okay, h is between 0 and 10. R and h are both in inches. Find the average value of the radius of the funnel. This couldn't be any easier, right? This couldn't be any easier of a problem because of what you know right here. The average value of a function. Well, they want the average value of the radius. So what's going to go right there? The radius function. And so this problem could not be any easier. And so part A, you're going to do the integral from what to what? 0 to 10. Because what's our input? Our input is h. The input of the radius function is h. This is r of h. So this would be like dh. So you could just write r of h. You don't even have to write it all out because they already defined it for you. It would be dh. It's with respect to h. H is your input. So h, it says right here, goes from 0 to 10. And then what am I missing? Divided by 10 minus 0. This is a calculator problem. And so you simply write that down, so let's all do it, get your calculators out. You go right to your calculator, and it's perfectly acceptable on the AP test to just put R of H. They've already defined it to be that, and you could write it. Now, obviously, on your calculator, you're going to have to type it out. Now, you could change it on your calculator to X's if you want, but you could do it with H's too. Can't forget to divide by 10, but you're going to get graded. My guess is this problem was worth 2 points, maybe 3 at the most. Might have been 1 point for setting it up and 1 point for the answer. Okay, it's possible they had 2 points for the setup, 1 for the integral, 1 for the 10 on the bottom, and then 1 for the answer. But it's possible it was only 2. Every free response question is worth 9 total. Okay, what do you get? 1.817. What units will we put on this? This is average radius, right? So that would be inches. 1.817. I don't know, just trust me that. Everybody else do that too. Okay. All right, so there you go. That's it. I mean, that's a great example. What I'm saying, 90% of the time, we're going to get a jump right to our calculator. So the biggest part of these kind of problems is recognizing that we need an integral, that there's a formula, or the integral is going to do this for us, and we just set up the integral, and boom, type it in. I really like these problems. I think these are a lot of fun. Especially compared to some of the old chapter 4 stuff we did, setting up those. I always think these are way easier to set up. If you just understand the underlying concept of what's going on, integrals are pretty darn easy to use. Okay, so that's an example of an average value function. Okay, where you're going to use that. Okay, let's go to the third thing. This is the big one. This is really the biggie right here. Okay, when you have the integral of an f prime, that can be an f double prime, whatever. But if you, and I wrote this down a while back, okay, for you. But this is a big one. First of all I've written is a basic fundamental theorem part 2, except I put f prime in there instead of f, okay? F outside instead of big F. But this is the big one. If you're doing the integral, the definite integral of a rate of change, that gives you the net amount of change. Well, think about it. Think about if the F prime was miles per hour, velocity. Then F would be miles. Well, F of B would be your ending position, and F of A would be your beginning position. And that's displacement. That's displacement. If you take your ending minus your beginning, that's your displacement. That's net amount of change. Okay, so the integral of a rate of change is going to give you the net amount of change. Think about it. It's your ending minus your beginning. That's the net change. Ending minus, well, I had this at the beginning, I had this at the end. You subtract those. That's the net change. Okay, let's go to 3C. Let's go to 3C in that package. Okay? All right, so now this is F, so it doesn't really matter here what F is. So how does this connect? It says find the absolute minimum value and the absolute max value of G on the interval -4 to 12. Now here's G right here. Okay? So what does this have to do with net amount of change? Okay, G is going to be the net amount of change. Well, here's what it has to do with. First of all, I'm going to ignore the 2 for a minute. I'm going to ignore the 2 because remember, we said the 2 just does what? What's that effect? The initial value. And so therefore, on the antiderivative graph, it measures what? It affects the plus C, right? The vertical shift. So the starting point. So when we talk about amount of change, if you started here and ended here, and then you shift that up, isn't the net amount of change still the same? Right? There's still the same distance from your beginning to your end. Okay? So I'm going to ignore that just for a minute. But remember when we would do this? Remember when we'd say, okay, well, let's plot the G graph. Now, you guys don't have to write this down right now. But let's say we went from -4 to 12. And let's say for right now, we don't know where to start. Now, we do know where to start because we know that left input. But let's say we didn't know where to start. Remember those problems? Right? And so what I'm here to tell you is this area, this would be a 2 by 4 triangle. 2 by 4 is 8. Half that is 4. This is going to be -4, right? So wherever my area graph is, I don't know, let's just pretend it's up here. Where's it going to go? In the first 2 units, I go this way. As I draw this from -4 to -2, where's this graph, the G graph, which is the area graph, where's it going to go? Jace? It's going to go down 4 because of that area right there. Now, what's this area right here? +4. What's this area? What's this big area right here? That'd be 4 by 4. That's 16. This would be 8. If I had a problem like this on the free response section, first thing I would do is go in and write these numbers in. Right here. These are going to be, because I can tell they're going to be useful somewhere. Okay, what's this? -8 right here. And what's this right here? -4. Right? So you tell me, just wait here, Bill. You tell me what's going to happen. Let's say we know this starts here. What's going to happen to this graph? It's going to go down 4, then what? Up 4, then up 4 more, right? So up 8, but I'm just going by each little piece. Then what? Up 8 more, then what? Now, it would be changing concavity. I'm not worried about that right now. Then what? Okay, so it went down 4, up 4 more, up 8. This was 8, right? This went up 8. Now it's going to go what? Down 8. So it's going to be back to the same level as this, and then down 4. Now right there, what's the net amount of change? The net amount of change is 0. Did we even care where the starting point was? Right? That left, does that matter? Because if I shift this graph up and down, right, all of those points will still be the same distance apart. You get what I'm saying? Okay? So the idea is, we can use this idea of the integral is net amount of change, the area is net amount of change. We can now use this to really help us in some problems. There was a multiple choice problem a while back where I said it'll be a lot easier when we learn about areas. This is what I was talking about. As soon as you see a graph like this of f, and you're going to talk about the area graph, the antiderivative graph G, the antiderivative graph, the area graph is just going to go up and down by what those areas are. That's what those areas represent, the net amount of change. So this tells you right away, this graph's going to go down 4, then up 4, then up 4, then up 8, then down 8, then down 4. Okay, now you guys think about this while I get algebra. Think about the question now. Find the absolute minimum and maximum value of the function g. Which one would do we? 3. Yeah. Okay, do you see how knowing that now is going to help you with a max and min, absolute max and min? Now, here's the thing. You guys already knew this. I mean, because before, we would have thought of f as the slopes, right? If g is the area, remember I told you, when you see this, you right away think what? G is the area, yeah, but we said antiderivative, right? When we were doing area functions, when we learned that, we said, when you see this, you say g is the antiderivative, right? Which means f is the derivative, right? F is a derivative. So f is a slope. So we would have, before, we would have looked at this as, well, it's negative, so it's going to be going down, right? The slopes are negative, so it's going down. Then it's positive for a whole long time. So my guess is a lot of you on this question a while back would have said, well, it's positive for a whole long time here, so it's going to go up quite a ways, and that's going to be your max. And it turns out that's true. But it was a pretty inaccurate way of saying it, right? Because it was slopes, and you're like, well, it's positive, and how positive is it? Now it's easier to quantify that amount by doing area. It's still the same thing. We're thinking the area graph, and it's going to go up 4, then up 4 more, then up 8 more. That's a lot easier to tell how far up it's going to go than just say, well, the slopes are like 1, and then 2, and then 3. Does that make sense? It's just an easier way of knowing how much it's going to go up, see? So it's not like this is a brand new earth-shattering discovery that we're talking about here, but it just really refines something we kind of already knew, okay? So when you have a piece like this, you can really answer some max-min questions better because you can see that area. Yeah, that area is going to be big, and now, yeah, this is going to offset this, okay, but it was still going up, so that's going to be your max. So once you know that, you can say, okay, the max has got to be up here, and the minimum has got to be down here at -2. Well, now that means all you have to do is go, okay, g of -2. Now you could do, you're going to have to write out, you're going to have to justify this, and we talked about list of candidates. Well, where could the maxes be? Well, the max and mins could be wherever this is 0, so it could be there, could be there, could be there, could be there. It could be the endpoints, right? Could be there, could be there. Could be the endpoints or where the derivative is 0, right? We talked about that. All right. So you could do a whole list of candidates to justify, or you could just say, well, this, is going to be, a quick little G graph. I think it'd be pretty easy to draw. So we could do a list of candidates, but your max is going to be at your min's going to be at g of -2. Well, what's that going to be? That's going to be the area. Now is when the 2 would get involved, right? Because you want to find the actual value. So 2 to -2, right? So we want to do that actual area right there. But what is that actual area? Remember, you're going backwards. So what do you got? -8, right? That's why having those numbers in there is nice. So the area from 2 to -2, that's going to be -8, okay? That's going to be your area. Now, it doesn't look like it on my picture, right? But remember, I didn't know where this was starting. Now, where do we know a nice point here? We know what? We know G of, what's the point we know for sure? G of 2 is, G of 2 is 0, right? The area from 2 to 2 is 0. So G of 2, now look at my G of 2. My G of 2 is way up there, right? So obviously this graph needs to shift down, so G of 2 be 0. That's why this point would be down here, actually, I think. Okay, now where's my max? G of 6, right here. And so G of 6 would be the area from 2 to 6. Well, the area from 2 to 6 is positive 8. Okay, from 2 to 6, and that would be positive 8. So there's my max. Here's my min. And then again, your justification, you could have done a list of candidates, you know, which you could argue you could have done without even doing all that I just did, right? We have a lot of ways to look at a max min problem like this. We really do, right? You could have said, well, max and min, absolute max and min has to be when the derivative is 0, derivative undefined, endpoints. Well, derivative is f. It's never undefined. Derivative is 0, boom, 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 and the endpoints. And you could have made a list. You could have found all those areas, right? That would have been fine. Okay, but another justification could have been this. But again, the reason I'm really pointing this out today is I want to talk about this net amount of change. The net amount of change. Knowing these areas tells you. See, so right away I knew, well, this is changing. This is going to go down 4, then up 4. Right back to where it started. That's going to go up 4 more, then up 8 more, but then down 8, down 4. That's how I knew this was going to end up exactly where it started, because that area overall is 0. That overall area is 0, so that's the net amount of change. Okay? All right, let's see that in context in just a couple more situations. So now I've got this, I've just got some examples, whether you write this down or not, it's up to you, but I've got some examples of this. So this is still number 3. So rate of change, net amount of change. So what if you had miles per hour? So what if you had x prime, and that was miles per hour? Well, that's the net miles traveled from 0 to 3, net change in position. Because think about it, if that's x prime, which is velocity, then that'd be x of 3 minus x of 0. X of 3 minus x of 0. Okay, it'd be your position at 3, the end, and your position at 0, the beginning, subtracted. That's your net change. Okay, in miles. What if it was acceleration here? What if it was miles per hour squared? Well, the antiderivative of that is miles per hour. Notice I also put a little, I said, remember, our dt is like our width now. We can almost think of that as having units. Miles per hour squared times hours, that'd be miles per hour. We already kind of know that, right? Antiderivative miles per hour squared would be miles per hour. That's net change in velocity. That makes sense. You can have a change in velocity. If you're accelerating, your velocity is changing. So what's your net? This is your rate of change of velocity. This is your net change of velocity. Your velocity at the end minus your velocity at the beginning. Right? Because if it's x double prime in the integral, it's x prime when we do the fundamental theorem. So it's going to be velocity at the end, velocity at the beginning, subtracting, it's a net change of velocity. Okay? How about you're selling something, you're doing the profit. This would be the rate, it's called the marginal profit actually. We learned that back in chapter 4. The marginal profit's at dollars per unit. When you do the antiderivative, it's profit. It's your net change in profit. That'd be profit for selling 3,000. Profit for selling none. That'd be your net change. I mean, zero's kind of silly in that case. But anyway, that'd be your net change in profit. Okay, for selling so many units. So those are just some examples of a net change scenario. Okay, so we got a couple more of these. Notice how many there are in this 2016 packet. Okay, so let's go to 2C. Let's go back here to 2C. Okay, let's talk about this. Here's a particle. The velocity is given here. This is a calculator problem, so you have your calculators ready. The particle is at position 2 at time 4. How should I write that? The particle is at position x equals 2 at time t equals 4. Come on, how should I write that? X of 4 equals 2. right? The x function would be our position function. Often it is, whenever we're talking about a part moving on the x-axis. X is going to be our position function, okay, at time 4. Find the position at time 0. So what are they looking for? X of 0. Is there anything we could think of that we've been working on that would involve x of 4 and x of 0? Say it, Jaden. The integral of what? V, because V is what? X prime, right? Since V is X prime, right? That would be this, and that would be the same as that, and if we did the integral from 0 to 4, right? If we do the integral of V from 0 to 4, that would equal X of 4 minus X of 0, right? We got to understand what that integral would give us. There you go. Well, that's our calculator. We could just type that in. Anytime you set up an integral and they're letting you use your calculator, boom, you go with your calculator, you can get it. So, what do we know here? We know this. We can get it on our calculator. They told us this. Doesn't that mean we can find that? Right? In other words, what they've said is here's your integral, here's your velocity, and here's your ending point. It ends at time 4, it ends at 2. You find the beginning point. Okay? So that's how we would use the integral here. So we could have solved for this first, right? But we can find this integral, and then what do we want to do? We just want to take 2 minus that. We just want to take 2 minus that integral. What do you get? So do the integral of V, this right here, from 0 to 4, and then just do 2 minus that. Or just type it that way the whole time, right? Because that's what we're trying. We're trying to find x of 0. Trying to find x of 0. So if I add x of 0 over to here and subtract the integral here, so I'll have x of 4 minus the integral. So 2 minus the integral will give me x of 0. What do we get? Negative 5.219. Is that the integral, or is that when you subtract it from 2? Now, I kind of went through that kind of fast. Let's back up a minute. Before we learned about integrals, what would your thought process have been? Here's a velocity. They give me like an initial condition, and then they ask me for the position somewhere. What would have been their thought process? We learned this way back in chapter 2 with some simple ones. If they give you the velocity and you want to get the position, you would do, now stay with me here, you would do the antiderivative, which would have a what tacked on? Plus c. How can we find that plus c? Take the initial condition, plug it in, find the c, that would give me the position function, and then I could have put a 0 in. Are you with me? That's how we could have attacked that. One minor problem. Why wouldn't that have worked here? You can't do the antiderivative of that function. There's no antiderivative. Do you try it? There's no antiderivative of that function. See what I mean? So, yes, that would be an okay way to do it. I don't want you to forget about that. If you read a problem like that, I'd be okay with you saying, oh, okay, velocity, and they're asking me about position. Okay, antiderivative. So I'm going to do the antiderivative, do the plus c, And you're like, oh God, t squared, what would that be? Well, I got my calculator, let me try it. Oh, no antiderivative, right? Okay, that's a problem. So, you got to remember this, same thing. Is it the same amount of information? It's the same information, right? It's the same information, but we set it up as an integral. And, we got x of 4, we want x of 0, that'd be the integral of b, would give me x of 4 minus x of 0. The definite integral, this fundamental theorem part 2, comes in really handy so we can get it. Because we can do we can do a definite integral even if we can't do the antiderivative. Why? Because we got approximation techniques. That's what the calculator's doing, right? Remember, f of b minus f of a is only one of the 3 ways on the very first screen today. It's only one of 3 ways you can do a definite integral, is with the antiderivative. You don't need the antiderivative to do a definite integral. So the definite integral is more powerful than just doing the antiderivative. Okay, but don't forget about that. That would have worked. In some cases, that would have worked and been a fine way to do it. But it's not always going to work. Okay? All right. Powerful stuff. Now, what was the other one I said here? 1c. Let's go to 1c. So look how often the definite integral is showing up here. Now we got a table. Okay? 1c. Use your answer from part B. Oh, we had to do a Riemann sum here. Okay, did we do that already? Oh, we did it, but I didn't have this packet hammered out yet. Okay, we can do this pretty quick. It says use a left Riemann sum with 4 subintervals indicated by the table to do the amount of water removed from the tank during 8 hours. The amount removed from the tank. Okay? All right, so the amount removed from the tank would be, this is liters per hour, so that'd be the integral of R, because that's liters per hour, from 0 to 8. Okay? So that would be the amount removed from the tank. Net amount in liters. Okay, now we had to do a Riemann sum with 4 subintervals. So 1, 2, you guys remember this one? I put this one up here the other day and we just worked. Okay, so now we can go ahead and get our answer. So it's a left. So which values am I going to use? I'm going to have 1340 times, what's its width? What's the first width? 1 plus the next one, 1190 times 2 plus 950 times 3 plus times 2. Okay, those are going to be left because my first height is going to be 1340 with the 1, and then, right? So that's what we did the other day, right? We could have wrote f of 1 and then f of 0, f of 1, f of 3, f of 6. We could have wrote it that way, right? But, okay, go ahead and multiply that out, okay? And that's going to be your answer, and we won't worry about over underestimate right now. I think it was an overestimate because this is decreasing, so the left rectangles will be over. So I think that was going to be an overestimate. But go ahead and multiply that out, give that answer. Now, that was the total water removed during those 8 hours. Okay? Now, use your answer from part B to find an estimate for the total amount in the tank at the end of the 8 hours. Well, up here we have a function that says how fast the water is being pumped in. So what we need is to find out how much has been pumped in. We just found out how much has been removed. So how do we find out how much has been pumped in? Tell me what to write here. Starts with an I. The integral, yes, come on, everything we're doing is an integral, right? Come on. What's the amount of water pumped in is what we want. This is the amount per hour. This is liters per hour being pumped in. We want the amount being pumped in. That's an integral from 0 to 8 of W. Boom, that's it. That's it, right? It's too easy. That's the problem. These integrals are too easy. You're going to make them too hard. You're looking for something really hard. No, that's the rate it's being pumped in. The integral is how much is pumped in. The net amount. Okay, do it on your calculator. Here we go. There's a calculator one again. There's a calculator one. What do you got? Liters? Agree? Now, what was the answer in B? Liters. Sound right? Now the answer to C. We're not done with C though, are we? C is how much water's in the tank at the end of 8 hours. So what do we need to do? There's 3 numbers we need. 2 of them we just found. Where's the other number? Read the problem. There's 50,000 liters in there at the start. So we're going to take 50,000. Now we should show this. I don't have room here, so you should write this. Of course, you've got more room in below there. But we're going to take 50,000 and do what? Take away 8050. Add 7836.195. Now, it said the nearest liter. It said the nearest liter. Nearest liter. So we can take off this decimal. Nearest liter, 7836. See what they're doing? But that's simple. It was simple. We got to use our calculator. We just had to set up the integral. That's all we had to do. They gave us a function, told us it was liters per hour. All we needed was the integral, gave us total liters. It's so easy. And it's liters in, and the Riemann sum was liters out. So that's it. That's it. Right? That's it. You're going to want to make these 2 hard for some reason. Okay? All right, last one. This is quick. Number 4. It's another one we've kind of talked about already. Okay? But if you do the integral of the speed graph, okay? Okay, if you do the integral of speed, you get total distance traveled. But remember, speed is the absolute value of velocity. But again, this usually comes in handy, real handy, on calculator problems. All you do is you just throw absolute value bars around the velocity graph, you type it into your calculator, and away you go. But this is not net, this is total, so we got to understand why. So if I was doing a problem like this, and this was my velocity graph, I put it in red here, and this was -2, and this was 10, and this was -4, and this area right here, let's say, was, I don't know, 6. Okay? Now, if you added up the area, if you did the integral of the velocity, then that would give you 8, 4, 6, that would be 10, right? That would be your net distance traveled. So from your beginning to your end, you had a gain of 10. But if you want to do total distance travel, if you want to do that, then all of a sudden that becomes this graph. Right? Doesn't absolute value just turn everything positive? Wouldn't that dotted graph be the absolute value graph? That'd be the speed graph. You turn everything positive. Everything that's negative turns positive. Well, now what do you got? Now you got 2, you got 10, you got 4, and you got 6. So you got 12 and 10, you got 22. Isn't that your total distance traveled? See, this graph is saying you're going to go 2 left, then you're going to go 10 right, then you're going to go 4 left, then you're going to go 6 right. Well, that's going to change your net distance traveled, your displacement. but your total distance traveled is 2, 10, 4, and 6. And you add those up. So you just throw bars around the absolute value, and you've got it. Okay, so that's a really important one to remember when you hear the term total distance traveled. So we go one last time here to 2D. You may have seen it here. And so find the total distance traveled of the particle from 0 to 3. Well, they give you the V graph. So all you need to do is write this. All the work you got to show right here is you got to write that down. That's all you got to do. And now on your calculator, you go ahead and you just type that in. Now, remember to get the bars. It's not that vertical bar we use with the solve. You got to go to the where your derivative stuff's at, that template thing, where your derivative and intervals are. That's where your absolute value bars are. Okay? So you can't use the vertical bar that we use with solve. That doesn't work. Okay? What do we get? 5.301. Okay? That's it. It is really that simple. Find the total distance traveled. When you see total distance traveled, that's integral of the speed, which is the bar absolute value of velocity. Absolute value of velocity. That's all you got to do. Type in your calculator, get your answer. Okay, probably 2 points for that problem. Setup, answer. Okay, make sure you write the setup. All right. So, tabular data packet. Any question, anything you've run into that was a problem? I know I only gave you kind of some, well, I told you yesterday to start working on that. I don't know how much you did. But is there any of those that you've run into that's a problem? Because basically our assignment's going to be to finish this thing. Okay? You're going to see a lot of the similar kinds of problems that we just talked about. Now there's going to be some old derivative ones like just rates of change, like slope and stuff like that. Has anybody got one that they read about that they're stuck on? Okay, we may have that in this week, so let's get that done. Okay, so that's your number one goal, is to finish that packet right there. Let's get to work on that thing. Okay, hopefully you got a good start on that. You have some work. And then you can work in sample 3 if you get that done, but let's get that packet done. There's not a lot of grades left. I have a small daily grade to put in, and maybe this packet. We may pick up this packet, but I may pick up this packet. Good points for that. So.
I never got this tabular packet.
That is a problem. See, that's right here. I don't know what the question this is, might be, I have no idea. But in terms of temperature of the soup, explain the meaning of. So what do you think of right away? You see this integral right here. What do you think of? Especially with the 1/12. Average value, right? When you see 0 to 12 and a 1/12 out in front, right? That's average value of whatever that function is. Now it says that T, I think T is the temperature of the soup, right? And 12, that's probably an hour. So that is the average, whatever you find when you find this value, which you're going to do with trapezoidal sums. So you do a trapezoid to do the integral, and then you'll have the 1/12 that you'll multiply it at the end. Okay, remember your sums, your lefts, your rights, your whatever, they do the integral, right? You find the integral with those. And then, if there's a 1/12 or something out there, then you have to do that. But whatever answer you get, that's going to be the average temperature of the soup over that 12-hour period or whatever those units are. Okay?